Clean energy is absolutely essential for our future, right? We all know this. But, every energy system has a hidden kind of heavy side. What exactly happens when these massive hurricane-proof machines wear out, or when toxic waste is just way too dangerous to leave lying around? Well, welcome to the energy afterlife. Wind turbines definitely don't spin forever. Carbon emissions don't just magically vanish. And nuclear fuel? Well, that leaves behind some pretty serious radioactive ghosts. We're building clean tech at a literal breakneck pace, so the big question is, how do we engineer our way out of the inevitable mess they leave behind? In this explainer, we're going on a journey through 3 entirely different states of waste. We've got massive physical trash piling up on the surface, invisible greenhouse gases floating in the air, and extremely hazardous materials buried deep, deep underground. All right, let's dive right into our first massive challenge, the wind turbine dilemma. So those giant wind turbine blades, they're engineered to withstand brutal hurricane-force winds, but they do reach the end of their working lives, and right now, they're mostly just piling up in landfills. By 2050, we are literally looking at 43 million tons of global turbine blade waste. Picture thousands of Eiffel Towers, but made entirely of solid fiberglass. It's a colossal environmental challenge for sure, but hey, it's also a massive industrial opportunity. And this is where we hit a classic GCSE chemistry problem. These blades are incredibly tough, specifically because they're made of fiberglass, tightly bound by things called thermoset resins. Because these resins form permanent, cross-linked molecular networks, they actually burn rather than melt. So you can't exactly just toss them into your standard recycling bin. But human engineering is stepping up with some genuinely gritty, real-world solutions. We're literally shredding old blades to use as concrete filler. We're also tossing them into 1400-degree cement kilns, which actually offsets coal use and reduces the carbon emissions from cement production. Oh, and we're developing advanced thermal breakdowns too. One of those advanced methods is called pyrolysis, and it is fascinating. Companies are using intense heat in a completely oxygen-free environment. Now, because there's no oxygen, the materials don't actually catch fire. Instead, the organic resins chemically break down into useful gases, which allows us to recover raw 99.9% pure glass fibers that are perfectly ready to be used all over again. Looking forward, though, the industry is totally revolutionizing how these blades are made in the first place. Next-generation blades use advanced materials that act like thermoplastics. So unlike those old cross-linked resins we just talked about, these can actually be melted down, chemically dissolved, and molded perfectly into the next generation of wind farms. It's a total game changer. Okay, moving on from solid trash, let's talk about capturing the invisible waste. We're talking about carbon dioxide. For heavy industries like cement and steel that still have to rely on burning fossil fuels, their waste goes straight up into the sky. The proposed engineering fix for this is called carbon capture and storage, or CCS for short. The whole idea is trapping the CO2 right at the smokestack before it ever has a chance to escape into the atmosphere. It sounds pretty simple in theory, right? But it is a massive physical operation. We capture the gas, then compress it so intensely that it enters what's called a supercritical state. Basically, it gets squished until it acts like a super dense liquid. Then, it's fired through high-pressure pipelines and pumped deep down into porous rock layers or old, depleted oil fields. But there is a major catch. Capturing and compressing all that gas takes a colossal amount of power, and we call this the energy penalty. Get this, a power plant might need up to 180% more energy just to run the capture equipment. So you end up burning way more fuel just to capture the emissions of the fuel you're already burning. Kind of wild, right? And we really have to look objectively at how this captured carbon is mostly being used today. Right now, about 80% of it goes towards enhanced oil recovery. It's pumped underground to basically squeeze the very last drops of oil out of depleted wells. It definitely stores the carbon, sure, but it yields more oil, which, you guessed it, leads to more emissions when it's eventually burned. All right, time for our final descent. Welcome to the ultimate time capsule. We're going deep underground to deal with the most hazardous, long-term waste of all. Nuclear power is amazing because it generates an incredible amount of steady, low-carbon electricity, but it leaves behind highly radioactive, spent fuel rods. And these demand an eternal storage plan. We absolutely cannot just leave them sitting in cooling pools on the surface forever. So, the leading global scientific consensus for handling this is the Deep Geological Repository. Imagine a highly engineered, massive vault excavated into ancient, stable rock, a full kilometer below the surface. Places like the Onkalo facility in Finland are actively paving the way to make this sci-fi sounding concept a total reality. The goal here isn't to make the radioactive waste just magically disappear. The goal is complete and total isolation. We lock the waste away using redundant barriers. We seal it in extremely thick copper canisters, wrap those in water-absorbing bentonite clay, and then encase the whole thing in millions of tons of solid granite so it literally never reaches the biosphere. But before we bury it all, there's this fascinating new recycling tech on the horizon called partitioning and transmutation. Scientists can actually chemically separate the most dangerous, long-living radioactive isotopes and use them as fuel in specialized fast reactors. This essentially burns up the absolute worst of the waste, massively shrinking the final volume that we actually have to bury. And this tech is becoming super critical as the world looks to deploy thousands of small modular reactors, or SMRs. While they're heralded for being incredibly safe, some of them use totally different coolants, like molten salts or liquid metals. That means entirely new types of spent fuel chemistries that your generation is actually going to have to figure out how to manage and recycle. Which brings us to our final thought: building a circular future. The challenge of the energy afterlife is absolutely colossal, but human engineering is already building the mechanical shredders, the high-pressure pipelines, and those deep rock vaults to meet it head-on. So as we transition our global economy, we really have to ask ourselves, are the gritty compromises we're making today, like shredding blades into cement and burying carbon underground, the exact stepping stones we need to eventually build a perfectly circular tomorrow? It's a massive scientific challenge, and it's one we are absolutely going to solve.